22 hours and 32 minutes. That is how long it takes a single radio signal from Voyager 1 to reach Earth right now, traveling in one direction at the speed of light. You would expect a machine that far away, launched all the way back in 1977, to have already gone quiet years ago, but it hasn't, not yet. And that is not even the strange part. Stick around, because the real story here isn't that Voyager 1 is still alive. It's that when it finally does go quiet, NASA has admitted, plainly, there is no backup plan. Now, before we get into why that is such a big deal, hit subscribe if you want to be here the moment the last signal from Voyager 1 ever reaches Earth, because when that day comes, we will be covering it as it happens, and you will not want to hear about it secondhand. Let us go back to where this story actually begins, because before we talk about endings, we need to talk about how strange this beginning really was. Here is the situation in plain terms. Voyager 1 is a spacecraft the size of a small car. It left Earth in 1977, before most of your parents were born, and it is now more than 15 billion miles away, farther from us than any human-made object has ever traveled. It is not orbiting anything. It is not coming back. It is flying, alone, through the space between the stars, and it is powered by a chunk of decaying metal that loses a little bit of energy every single year, with no way to refuel it, no way to repair it, and no way to send anyone out to fix it. Engineers on the ground are managing its slow decline the way you might manage a candle burning down in a room with no more candles left. That is the story we are telling today, and it is stranger and sadder and more amazing than most people realize. Let us start from the beginning, because to understand why there is no backup plan, you first need to understand what people usually get wrong about this spacecraft. Most people assume Voyager 1 will just switch off one day, like a light bulb, all at once. That is not what is happening. What is actually happening is slower and, honestly, more dramatic. For more than a decade now, engineers back on Earth have been reaching into the spacecraft system, one instrument at a time, and switching things off on purpose, permanently, just to keep the rest of it breathing a little longer. It is not a sudden death. It is a long goodbye, instrument by instrument, and we are watching it happen in real time. To really get why this matters, we have to go back to a moment when almost nobody believed this little spacecraft would matter at all. In the mid-1970s, NASA was planning a rare alignment of the outer planets, a lineup of Jupiter, Saturn, Uranus, and Neptune that only happens once every 175 years, where a spacecraft could use each planet's gravity like a slingshot to reach the next one. It was a strange, once-in-a-lifetime opportunity, and yet Voyager almost did not happen the way it was originally imagined. The full grand tour to all 4 planets was considered too expensive, so NASA scaled the mission down and told the public, quietly, to expect a mission that would last about 4 years, mostly focused on Jupiter and Saturn. 4 years. Nobody involved in building it thought they were building something that would still be sending signals home nearly 50 years later, let alone something that would outlive its own creators' careers. That is the underdog setup, and it matters because Voyager 1 was never supposed to be a legend. It was a budget mission, trimmed down, built with the technology of a world that still used cassette tapes and rotary phones. Its onboard computer has less processing power than the key fob you use to unlock your car. And yet this modest, underestimated machine ended up rewriting what humans understood about the solar system, and then kept going, past the point anyone expected it to survive, into a place no human object had ever been before. So how does something built with 1970s technology keep running for nearly half a century in the freezing dark of deep space, far beyond where sunlight is strong enough to power anything? The answer is a device called a radioisotope thermoelectric generator, which sounds complicated, but the idea is simple. Picture a small block of decaying radioactive material, plutonium-238, that gives off heat naturally as it breaks down, the same way a dying campfire still gives off warmth long after the flames are gone. Voyager 1 converts that heat into electricity. There is no sunlight involved, because past a certain distance, sunlight is too weak and too far away to power anything useful. This heat source does not need light at all. It just needs to decay, and it has been decaying, slowly, every single day, since before the spacecraft even launched. Here is where the first surprise comes in, and it is one most people never hear about. Engineers expected the radioactive core to lose its punch on a predictable, well-understood schedule, since the physics of radioactive decay is extremely well known and follows precise mathematical laws. What they found, once decades had actually passed, was that the electrical output was dropping slightly faster than the pure decay math alone would predict, likely due to slow, tiny changes inside the thermoelectric materials that convert the heat into usable electricity. It is a small difference, but a real one, and that small difference means a spacecraft that already had a shrinking power budget has an even tighter deadline than the original engineers assumed. Every year, Voyager 1 loses about 4 watts of electrical power. 4 watts. That is less power than the small bulb that lights up the inside of your refrigerator when you open the door. That tiny sliver of power, year after year, is the whole reason instruments are being shut off one by one, and it is the whole reason there is no backup plan waiting in the wings. I want you to sit with that comparison for a second because it is almost unbelievable. A machine currently more than 15 billion miles from Earth, traveling through freezing interstellar space at over 38,000 miles per hour, is being kept alive by roughly the same trickle of power as your fridge light. That is the entire operating budget for one of the greatest scientific achievements in human history. And every single year, that already tiny budget gets a little smaller. Before we go further into what scientists actually found out there, I want to ask you something. What part of this story surprises you the most so far? The age of the spacecraft, the size of its power source, or the fact there's no way to fix it? Drop your answer in the comments because it genuinely helps me understand which parts of stories like Voyager's people want to go deeper on next time. Now let's talk about what Voyager 1 actually discovered, because the shrinking power supply is only half the story. The other half is what this fragile little machine managed to find along the way, and the first major discovery genuinely stunned the scientists watching from Earth. When Voyager 1 flew past Jupiter's moon Io in March of 1979, researchers expected a cold, dead, cratered rock, similar to our own moon. What they actually found, captured in images sent back across hundreds of millions of miles, was a moon covered in active volcanoes, spewing sulfur high into space, making Io the most volcanically active body ever observed in our solar system. Nobody had predicted that. The compressed version of that shock is simple. A supposedly dead moon turned out to be the most violently alive place scientists had ever pointed a camera at. Between those two flybys, there was a smaller discovery that still surprised the team, one that rarely gets talked about. Scientists expected Jupiter's ring system, if it even existed at all, to be faint and unremarkable, since nobody had detected clear evidence of rings around Jupiter from telescopes on Earth. What Voyager 1 actually found, in March of 1979, was a thin, dusty ring circling the planet, invisible from Earth but very real up close, made of fine particles kicked up by micrometeorites striking small nearby moons. It was a quiet discovery, easy to miss next to the volcanoes of Io, but it told scientists that rings might not be rare at all. They might simply be too faint for older telescopes to catch. Compress that surprise down to something familiar. It was like checking a room you were told was empty and finding a fine layer of dust hanging in the air. Dust that had been there all along, just too thin to notice until you looked closely enough. The second finding changed how scientists thought about entire categories of worlds. Voyager 1 also gave humanity our first truly close look at Saturn's moon Titan, and scientists going in expected a frozen, mostly featureless ball of ice. What the spacecraft found instead was a moon wrapped in a thick, hazy orange atmosphere, thicker in some ways than Earth's own atmosphere, hiding a surface that later missions would show has lakes and rivers, just made of liquid methane instead of water. Imagine standing on a world where the sky glows warm orange instead of blue, and the rain falling around you is not water at all. That single flyby helped convince an entire generation of scientists that strange, atmosphere-rich moons might be far more common and far more interesting than anyone had guessed. Try to actually picture the feeling of that place for a second, not just the facts about it. A thick, hazy orange sky pressing down low, cold enough to freeze the air in your lungs instantly, with a faint chemical smell if you could somehow breathe it, and a strange hush over everything, since the atmosphere there is dense enough to muffle sound in a way our thin Earth air never could. That is the kind of sensory detail that gets lost in a list of facts and numbers, but it is exactly what makes a place like Titan feel real instead of just theoretical. A genuine world instead of a data point on a chart. The third discovery is the one that puzzled scientists the most, and it did not happen near a planet at all. It happened after Voyager 1 had already finished its main planetary tour and just kept flying outward, deeper and deeper into the emptiness beyond Saturn. On February 14, 1990, at the request of astronomer Carl Sagan, who worked with the mission and later helped found the Planetary Society, engineers turned Voyager 1's camera backward, toward home, and took one final photograph before shutting the imaging system down for good to save power. In that photograph, Earth appears as a single pale blue dot, less than a pixel wide, suspended in a scattered beam of sunlight, floating in an ocean of darkness. Sagan later described it as a message about how small and fragile our home really looks from very far away. And that idea, that single fragile pixel, is still one of the most quietly powerful images ever produced by any space mission. Notice the rhythm here, because it repeats throughout this whole story. One moment we are talking about billions of miles and volcanic moons and orange skies made of methane haze. The next moment we are talking about a fridge light, or a car key fob, or a single photograph the size of a fingernail on your screen. That constant back and forth between the unimaginably huge and the completely ordinary is exactly how this mission has always worked, bouncing between cosmic scale and kitchen table scale, because honestly, that contrast is the only way our brains can begin to grasp distances this enormous. Let's talk about the moment Voyager 1 left the solar system entirely, because this is where the numbers start getting genuinely precise, and precision is where this story gets serious. For years, scientists working on the mission, including Ed Stone of Caltech, who served as the mission's chief scientist for decades, debated exactly where the edge of the solar system actually was. It is not a wall, it is not a line painted in space. It is a boundary defined by particles, by the outward pressure of our sun's solar wind pushing against the thin gas that fills the space between stars. On August 25, 2012, data started arriving that showed something had changed dramatically. The density of charged particles around Voyager 1 jumped by a factor of 40, almost instantly, in a way nothing inside the solar system could explain. Scientists had expected this transition, if it ever happened, to look gradual, a slow fade from one environment into another over months or years. What they actually found was closer to a sharp doorway, a rapid, dramatic shift in the particle environment happening within a matter of days. NASA confirmed the finding a year later, in September of 2013, announcing that Voyager 1 had become the first human-made object to reach interstellar space, the vast region between stars, filled with the leftover material from ancient supernova explosions. Compress that surprise for a second. Scientists expected a slow fade like a sunset. What they got instead was closer to a spacecraft walking through an actual doorway, closing one chapter of physics behind it and opening another, almost overnight. Here's something worth pausing on. What's it worth to you personally, hearing that a machine built when your grandparents were young actually crossed into interstellar space and is still talking to us? If this kind of discovery means something to you, hit like on this video, because it genuinely tells the platform that people care about this kind of deep space story, and that helps far more people find it. With that boundary crossed, the mission entered an entirely new phase, one focused less on planets and more on the strange, nearly empty region between stars, called the interstellar medium. And this is where the countdown on Voyager 1's power supply really starts to bite. Every watt matters now, because there is no sunlight out here strong enough to help, no nearby planet to swing past for extra momentum, nothing except that slowly decaying chunk of plutonium and careful, patient decisions made by engineers on the ground, back on a planet more than 22 hours away by radio signal. Picture the scale shift here for a second, because it is jarring every time. One paragraph ago, we were talking about a boundary 40 times more crowded with particles than the space just inside it, a genuine doorway between our solar system and the galaxy beyond. Now we are talking about heaters and watts and a control room where engineers quietly decide which instrument gets to keep running and which one has to go dark, the same way you might decide which lamp in your house to leave on during a long power outage. That is the whole rhythm of this mission. Huge discovery, small kitchen table decision, over and over for nearly 5 decades. Let's get specific about the numbers because the precision here really does tell the whole story. Voyager 1 launched carrying enough electrical power to run all of its scientific instruments comfortably, along with heaters to keep sensitive electronics from freezing solid in the cold of deep space. As the plutonium decayed year after year, and that 4 watts kept disappearing annually, mission engineers had to start making brutal choices. In 2007, they turned off the heaters and instruments related to the planetary science package, since the planets were long behind it and would no longer be studied. In 2019, they shut down heaters for the cosmic ray subsystem, one of the instruments detecting particles from deep space, and remarkably, that instrument kept working anyway, even at temperatures far colder than engineers had ever tested it for, which genuinely surprised the team. Then, in 2023, something happened that nobody on the mission team saw coming. Voyager 1 began sending back garbled, meaningless data, a stream of what looked like random ones and zeros instead of actual readings. For nearly 5 months, the spacecraft was technically alive and responding to commands, but the science and engineering data it sent back made no sense at all, like a person still breathing but unable to speak clearly. Engineers eventually traced the problem to a single corrupted chip in the flight data system, a chip storing a small piece of code needed to properly format outgoing data. That chip was likely damaged by a stray cosmic ray or simply by decades of wear, And the team, working with a computer language nearly 50 years old, had to write a workaround and painstakingly reprogram parts of that ancient memory from over 15 billion miles away, without ever being able to physically touch the machine. Think about what that actually looked like on the ground, back on Earth. A team of engineers, several of whom were not even born when Voyager 1 launched, gathered around old printouts and decades-old circuit diagrams, trying to reconstruct exactly how a computer system built in the 1970s stored and organized its memory. They had no way to open a panel and look inside, no way to swap out the damaged part, no repair truck to send. Every single test had to be planned out, written as a command, sent across that same 22-hour gap, and then another 22 hours had to pass just to see whether it worked. A simple fix that might take an afternoon in a repair shop on Earth instead took months of careful, patient guesswork, conducted entirely by radio across a gap of more than 15 billion miles. This is worth sitting with, because it captures the mystery at the heart of this whole story. Scientists will tell you they do not fully understand exactly why that particular chip failed when it did, whether it was radiation, age, or something else entirely. And this kind of failure is still debated internally among the engineering team, since Voyager 1 was never designed to run this long in the first place. There was no manual for this. Nobody who built the spacecraft in the 1970s wrote instructions for keeping it alive in its fifth decade, because nobody believed it would need them. Every fix from here forward is engineers essentially improvising, using decades-old documentation, educated guesses, and enormous patience to keep a fragile, aging machine breathing just a little longer. That brings us to the real heart of today's question. Why is there no backup plan? The honest answer is almost uncomfortable in its simplicity. There is no second Voyager 1 sitting in a garage somewhere ready to launch and catch up. Building a spacecraft, testing it for years, and then flying it for nearly 5 decades just to reach the same distance and the same scientific position is not something you can simply repeat on demand. Voyager 1's sister spacecraft, Voyager 2, launched slightly earlier in 1977, but took a different, slower path through the outer planets. And while it also crossed into interstellar space in November of 2018, it is traveling in a completely different direction, sampling a completely different slice of the space between the stars. It is not a replacement. It is a second, separate observation point, and it has its own shrinking power supply counting down as well. It also helps to understand just how differently spacecraft are designed today. Modern probes are usually built around solar panels, since solar technology has improved enormously since the 1970s. But solar panels become nearly useless once you travel far enough from the sun, which is exactly why Voyager 1 was given a radioactive power source in the first place. Building a new radioisotope thermoelectric generator today is not simple either, since the specific type of plutonium used requires special production, and global supplies of it have historically been limited, shared carefully between a small number of missions that each need it for their own power systems. Newer missions, meanwhile, are not built to replicate what Voyager 1 does. Modern spacecraft study nearby planets, distant exoplanets around other stars, or specific targets like asteroids and comets. But almost none of them are designed for the specific job of physically flying through and directly sampling interstellar space itself, the actual material drifting between star systems. NASA has discussed potential future interstellar probe concepts, and in fact, a mission study group involving Johns Hopkins Applied Physics Laboratory has explored what a purpose-built interstellar probe might look like. But even in the most optimistic timelines discussed in early mission planning documents, such a probe would not launch for years, would take decades to simply reach the boundary Voyager 1 already crossed back in 2012, and would arrive at an entirely different position in space, sampling different material. There is no fast way to replace 50 years of momentum and distance. Time, in this particular story, cannot be bought back. So here's where we stand today. Engineers continue turning off instruments, one at a time, prioritizing whichever ones still have the most scientific value left to give. Current estimates from the mission team suggest Voyager 1 may be able to keep at least one instrument running into the early 2030s, though that estimate shifts slightly every time engineers reassess the power curve. Even after every scientific instrument has finally been switched off for good, the spacecraft's transmitter can likely keep sending a bare, simple signal home for a short while longer, carrying no science data at all, just a faint confirmation that it is still there, still functioning, still listening for instructions it may never receive again. Eventually, and this part is not really in question, the power will simply run too low to keep the transmitter itself broadcasting, and Voyager 1 will go silent. Not because it broke, not because it failed, but because it quite literally ran out of the tiny, decaying trickle of power that ever let it speak to us in the first place. Before we close things out, I have one more question for you. If you know somebody who would find this story about a 50-year-old machine still whispering back to Earth genuinely fascinating, would you consider sharing this video with them? Sharing helps stories about missions like Voyager 1 reach people who might never otherwise hear just how remarkable this spacecraft's journey really is. There is one more piece of this puzzle worth mentioning before we bring it all together, because it adds a strange kind of comfort to an otherwise sad ending. Even after Voyager 1 finally falls silent, whenever that day actually comes, the spacecraft itself does not stop existing. It does not burn up, it does not crash, because there is nothing out there for it to crash into. It will simply keep drifting, silently, forever, carrying with it the golden record, a phonograph disc bolted to its side containing greetings in 55 human languages, samples of music from cultures across the globe, and recorded sounds of Earth itself, including whale calls, thunder, and a human heartbeat. Ed Stone once described the record as a message meant to outlast our entire civilization, since Voyager 1 is expected to keep drifting through the galaxy for billions of years after everyone currently alive on Earth is gone. In roughly 40,000 years, it will pass, at a great distance, near a star in the constellation Camelopardalis, still carrying that message, long after its own voice has gone quiet. Think about the sheer contrast packed into that one object bolted to the side of the spacecraft. A gold-plated copper disc, smaller than a dinner plate, carrying the sound of ocean waves crashing, the sound of wind moving through trees, a mother's laughter, footsteps, a rocket launch, and beneath all of it, a single, steady human heartbeat, recorded and pressed permanently into grooves that will physically outlast the pyramids, outlast every language currently spoken on Earth, outlast the sun's current stage of life by many times over. Long after every device you own today has been forgotten, that heartbeat will still be out there, drifting silently between the stars. That single fact might be the strangest twist in this entire story. A machine we built to explore our own solar system, using technology older than most of our parents, is now a permanent, silent messenger, carrying pieces of who we were out into a galaxy that will likely outlive every trace of us here on Earth. We began this story with a signal, 22 hours and 32 minutes old, arriving from a spacecraft you might have assumed had already gone silent years ago. Now you understand why that signal is such a small miracle, arriving not because engineers solved this problem once and moved on, but because a small group of people keep solving it again, quietly, year after year, with a power budget smaller than your kitchen stove light, using a machine nobody expected to survive this long in the first place. What you now know, that you probably did not know 20 minutes ago, is that this is not a story about a spacecraft slowly dying. It is a story about how long something can keep speaking, even after almost everyone has decided it should have gone quiet. Voyager 1 was never supposed to leave the solar system. It was never supposed to still be listening to us, or answering back, in the year 2026. And yet, somewhere out past 15 billion miles of freezing, empty dark, a machine built by people who are mostly retired now, or gone, is still turning starlight-thin trickles of power into a whisper that reaches Earth, faithfully, 22 hours and 32 minutes after it leaves. There is something almost stubborn about that, if you really think about it, the way a machine with no consciousness, no feelings, and no awareness of its own fragile situation just keeps doing the one job it was built for, quietly, faithfully, long after everyone expected it to stop. One last question before you go, and I would genuinely love to know the answer. When Voyager 1 finally does fall silent for good, do you think that moment should be treated as an ending, or as the beginning of its real journey, the one it takes without us? Leave your answer in the comments, because it helps me understand how people actually feel about a story like this one, not just what facts they remember from it. Someday, maybe not for a few more years, that signal will simply stop arriving. There will be no dramatic final message, no countdown, just an expected transmission that never quite shows up, followed by silence where a signal used to be. And when that day comes, somewhere in a control room on Earth, a small group of engineers who spent years of their lives listening for a whisper across 15 billion miles will sit with that silence for a moment before turning their attention outward, toward whatever comes next. Think, for a moment, about everything that has to go right just for this story to still be happening at all. A radioactive core has to keep decaying at a steady, reliable rate. A 50-year-old chip has to keep holding its memory, cold and untouched, in a place colder than anywhere on Earth. A team of people, most of whom will not be working on this mission by the time it truly ends, has to keep passing the responsibility down, carefully, to the next generation of engineers, the way you might hand off a candle so its flame never actually goes out. None of that was guaranteed. None of that is even ordinary. It is simply, quietly kept happening, year after year, far longer than anyone ever expected it to. We open tonight with a signal, 22 hours and 32 minutes old, arriving from a machine most people assumed had gone quiet long ago. We close now with a different feeling entirely. Not surprise, but something closer to quiet respect for a small, aging spacecraft that keeps finding a way to answer, even when almost nothing about its survival makes obvious sense. Until then, it is still out there, still speaking, still carrying its fragile blue dot photograph and its recorded heartbeat farther from home than anything we have ever built, and it is still, somehow, right now, listening for us to answer back.